Now please welcome to the stage, Lawrence Forsley.
Well, I want to thank the conference organizers, the Anthropocene Institute, the sponsors, and Carl Page in particular for putting together this lovely show here. And I'm especially appreciative of the new conference mascot, Studley, who has been watching over us very carefully. I'm going to talk about contamination, transportation, or transmutation in LENR material analysis. So my outline, look at the raison d'etre, the material assay techniques, both nuclear and non-nuclear. I'll look at 2 electrolytic experiments, then raise the question, what was happening? Contamination, transportation, or transmutation, and some conclusions. So the raison d'etre. The hallmark of low-energy nuclear reactions is excess power. LENR excess power is often correlated with helium production or leaves a tritium ash. And there are often other nuclear reactions that have been detected either during or after the device operation, including transmutation. The difficulty is knowing what was in the background when the experiment began and correctly identifying any of these new particles. And the products are necessary to elucidate what the nuclear exit channels are. So this talk is going to concentrate on the post-run material assay techniques and their use in 2 different electrolysis experiments. So first of all, I'll go through some of the material assay techniques that at least I'm familiar with. Non-nuclear material analysis, so XPS, X-ray photoelectron spectroscopy, only works for the surface about 10 nanometers deep, but it does measure binding oxides, and it has about 100 part per million sensitivity. What's in green are what I consider to be positive attributes. What's in red are things that are either not positive or make it difficult to do the measurements. SCM-EDX, scanning electron microscopy, electron dispersive X-ray analysis. And again, this will work from about boron out to uranium, surface or near surface, and it's typically parts per thousand, not a lot better than that. The good news is that if you start seeing something that shouldn't be there, there must be a lot of it there. Then you can go to ICP-OES, inductively coupled plasma optical electron spectroscopy, otherwise known as atomic emission spectroscopy. It'll handle elemental lithium out to uranium, parts per billion, but there's some elemental interferences, and the sample prep reduces the sensitivity. And then you also have hydride interferences. ICP-MS, which is inductively coupled mass spectroscopy, covers the same range, but it has other interferences that you have to worry about between, for example, nickel 64 and zinc 64, and again, hydride and argon interferences. And as we found in the past at the Naval Research Lab, some of these instruments, such as the Finnegan, will favor higher A for a given Z. And then there's TOF-SIMS, time of flight secondary ion mass spectroscopy, isotopic from hydrogen isotopes all the way through uranium and higher, very high sensitivity on the order of 10 parts per billion, surface, but the problem is it's qualitative and you typically have a very small area that you're looking at. So some of the nuclear material analyses that we've done, liquid scintillator alpha-beta spectroscopy, low specificity but high sensitivity, very good way to detect tritium in an aqueous solution, low spectral resolution, X-rays and gamma rays, the gold standard being high purity germanium, lanthanum bromide then, sodium iodide, and finally gamma tubes, which will also detect betas. It has a very high specificity, and again, we like HPGE, but we also have to worry about background interferences. Neutron activation analysis, it is very good, high sensitivity for specific isotopes, but again, you can have an interference from your matrix, and again, not all isotopes, and the sample will become radioactive in some cases. And then solid-state nuclear track detectors like CR39. These have the advantage of being an integrating detector that means you can detect low flux. You can detect charged particles over 100 keV, nearly 100% efficiency, although neutrons, it's about 10 to the minus 3 to as low as 10 to the minus 5. And it works best in vacuum, but we have used it in aqueous solutions, provided you keep the temperature below about 50 degrees C because it begins to self-etch. So the first experiment, I call this Back to the Future. We conducted this at the University of Rochester, literally within eyeshot of John Heisinger's office in Hutchison Hall. It was a palladium deuteride electrolysis. I did this with Jacob Journet in the Department of Chemical Engineering. Eugene Maloff provided us Tanaka precious metals palladium. And we then planned on doing accelerator mass spectroscopy to measure the palladium isotopes afterwards. Unfortunately, John Heisinger said this was bad science, so we never got to do that part of the experiment. This was conducted under a grant from Eneco, courtesy of Fred Yeager. And this work was published in ICCF24. So looking at the details, using Tanaka precious metals plate, we took a 1 inch by 1 inch, 2.5 by 2.5 centimeter, split it into 3 pieces, working with one that was 1 centimeter by 2.5 centimeters by 1 millimeter thick. We ran the cell for a couple weeks at the University of Rochester, and we collected the reaction gases in a Summa canister. We analyzed it, but we had ambiguous results, so we discounted those. We then took the SEM EDX analysis and conducted that recently at the NASA Glenn Research Center. So looking at some of this material, SEM picture on your far left, and you notice there are lines. This is from polishing of the plate before we even received it. And if you look at the SEM EDX spectra, you'll find out that, first of all, looking at the palladium L series, it's pretty uniform. And if you look over on the side, it's mostly palladium with some carbon and oxygen. Now, when we run this, we find a very different structure on the surface. And as we go through the oxygen K series, carbon, silicon, lead, silicon, platinum, and we find that we've got a change in all of these. We've increased the oxygen, the carbon, the tin, the lead, the silicon, and the palladium has gone down. Clearly, we've had something unusual happen here. And if we look at the detail of the SEM EDX spectra, well, everything oxidizes when you get it out in the air. And we use carbon-carbon tape to hold the sample. And aluminum may be from the stub that we mount the tape on, that we mount the sample on. We also can get reflections from within inside the chamber. And if you look on the chart on the right-hand side, you'll see this comparison. And again, a lot of oxygen, a lot of carbon, but there's tin and lead and silicon and a little bit of palladium left over. Well, we'll look at a different site. Now, there's a hill up at the top there. And what it does is it shadows below it. So we can't see in there. The X-ray detector is shadowed. What's happening is you've got the electron beam coming in from one angle, you're viewing the X-rays from another angle, and shadowing is often a problem with an irregular, non-flat surface. And at the resolutions of a few microns or lower, you're always going to have shadowing. And again, the hill is just an inclusion on the surface. Looking at this site, we have a very different set. We've got 56% carbon, 41% oxygen, a little bit of lead, a little bit of tin, and a little bit of silicon. So where you look on your sample makes a difference. Now, comparing the two of these, the virgin piece that had never been hit, the piece that we electrolyzed, but we have to note the experiment had the following. We used a borosilicate glass container that contains boron, oxygen, sodium, aluminum, silicon, and potassium. There's a copper feed wire, and it's soldered with a tin-lead solder. And the ratio that we have of these is very similar to what solder is, standard 60-40 solder. We also have lithium sulfate in our electrolyte, but lithium and boron have low Z, and they're hard to see with EDX. It's also maintained in an aluminum calorimeter. Now, one could argue that although we had an aluminum stub and carbon-carbon tape, they probably should not have been viewed in the small area that we were looking at. But what about the calcium, the chromium, and the zinc? The zirconium. Second experiment. This is using a proton-conducting ceramic encapsulated in thorium and uranium, and run in a what's called a Rifex electrolysis system from SETI down in Florida. And this was run at NRL in 1996. And I ran this with Bob August and Gary Phillips with the support of Dave Nagel. You may not remember this. So we did neutron activation analysis at the University of Illinois after we finished running these samples. We also did SEM EDX, and we also did ICP mass spec at NRL. And this was funded by JWK Corporation. So looking at what we found, Jim Patterson at SETI and I made these ceramics. We ran the cell for only 4 hours at less than 0.2 amps. We did some real-time and afterwards high-purity germanium gamma ray analysis with Bob August, and then with Sheldon Landsberg at University of Illinois did the NAA analysis. So the ICP mass spec, we found increases in barium, nickel, lead, zinc, calcium, magnesium, and aluminum, and some trace amounts of chromium, iron, nickel, and platinum, and a decrease in uranium and thorium. But there were no isotope shifts from natural abundance. And there were only 1% to 2% isotopic shifts between the used and unused samples, well within 1 sigma error bars. Titanium was notably absent. We suspect what happened was it oxidized, and even though the way the setup was that there was a titanium plate as an anode and a titanium plate as a cathode, only the platinum wire itself was in fact involved in the electrolysis. The titanium became oxidized. The real-time work during operation showed no change in U-235 or daughters of the U-238 or the thorium-232 decay chains. We then took it out and we ran it for a long period, expecting to see the growing in of the lead and thallium lines, which we saw. The results were ambiguous with the NAA because we fissioned the uranium and the thorium, which also made it highly radioactive, and that was not good. And these results were published in ICCF. So some of the diagnostic issues, the inability to distinguish between nickel-64 and zinc-64. Did we enhance the nickel at the expense of zinc? We don't know. Furthermore, zinc-67 overlaps with doubly charged barium-134, so we can't report that. And contamination and transportation. EarthTech down in Austin, Texas had noted that O-rings, which are Viton, are a possible source of barium. And chromium, iron, nickel, and platinum were all present in the electrical feed wires and in the titanium electrodes. Similarly, aluminum and silicon were present in the aluminum pump head, which has caused us later to adopt a contactless peristaltic pump. And again, the NAA issue, we produced fission products, which made this not only hard to handle, but confused what was there before we fissioned the uranium and the thorium. So, contamination, transportation, or transmutation? It's a difficult one. The background contamination and transportation from elsewhere within the cell to what you're trying to run. The sample preparation and contamination, handling and the reagents, system transportation and contamination. Just getting the parts out and getting them over to whatever diagnostic you're using after the experiment. If you can get through all those, then you may have transmutation. But it's best if you have isotopic differences. We rarely see those. And the non-background X-ray and gamma lines, but we rarely don't have competition with those as well. And finally, energetic particle emissions, those occur infrequently in a lot of these systems. So in conclusion, know your experiment, know your diagnostics and instrumentation, have statistically significant sized samples, be aware of confounding interferences and backgrounds, loss of sensitivity through sample prep and its dilution. You can go from a part per billion ICP mass spec to parts per million or worse after you've diluted the sample and entered it into the instrument. And unrealized investigational bias. I mean, we all know what we're looking for. Is that what we find? Be suspicious. And be wary of the tale of looking for your keys around the lamppost because the light is better there. And I thank you. Anybody believe that?
Hi, Lawrence. Jorge here. I just have a question. When you mentioned that the sample changes its composition depending on when you look, did you also check the composition in multiple parts of the surface before the whole experiment happened?
Well, we did this with a virgin piece of Tanaka precious metal, palladium. We looked in a few different spots, and it seemed to be fairly uniform. We only looked, I think, at three places on the other piece that had been electrolyzed, and there was variation in there.
Thank you.
Hi. Do you have an opinion about the transmutation, the Biberian and Master Mateo type experiments?
I don't know. I haven't done the experiments, and I haven't analyzed their material. I think it's likely that it's probably real. Jean-Paul will owe me for that afterwards.
All right.
All right,
very
thank
much,
you.
Lawrence.